Hi. All right, quantifiers in programming. Let's get started. So just a quick little bit about myself. My name's David Barri. You'll often find me online pretending that I'm this cantankerous Cape Barren goose. I've published a bunch of open source Scala FP libraries. So for the past 6 years, I've been using Scala and FP pretty much exclusively, and it's been fantastic. On one side, I've got a startup of mine called Shipwreck, which is a software requirements online tool. So the front end is all Scala.JS, back end is all Scala. Everything there is FP, and honestly, I could not have managed that much complexity and have it be such high quality without functional programming and strong typing. So don't let anyone ever tell you that FP is not useful in the real world. On the other hand, I work with Simple Machines from time to time. They're an Aussie consultancy, very techy, not a body shop. They do a lot of Scala, very FP friendly. If that sounds appealing, get in contact with me and I'll put you in touch. Right, so the structure of this talk, we're going to talk about what quantifiers are, then we're going to introduce them into programming, look at some examples, and then end with a summary. And all code is in Scala. So yay or boo, depending on your perspective. Don't judge me. Okay, so what are quantifiers? So quantifiers are words, expressions, or phrases that indicate the number of elements a statement pertains to. So in other words, they're a description of quantity. So these are some colloquial examples of some, all, no, most people. They're all quantifiers. So there are two quantifiers that are used the most in math, logic, and programming. This is one of them. So this upside down A is the universal quantifier for all. So let's look at a logical statement. We're going to break this down. So for all, the X is a reference to an individual element. P in this example, I'm going to say, is a set of Bob's friends. You can interpret that as being P of A, meaning that A is a member of P. In other words, A is Bob's friend. The arrow is implication, if A then B, else true. Similarly, Q is a set of people with beards, and it's the same thing. Q of A means A has a beard. So if we try to turn this into something a bit more natural, each thing that's a friend of Bob's has a beard. And to make that completely natural, all of Bob's friends have beards. The second most common quantifier is this backwards E, existential quantification. So we'll look at a similar statement. So there exists an X. P is still a set of Bob's friends. This time we're going to use conjunction, so A and B. Q is still a set of people with beards. So a thing exists that's a friend of Bob's and has a beard. In other words, or at least one of Bob's friends has a beard. So when it comes to existential quantification, there are two criteria. There has to be at least one element, and that value has to be unknown. And that value being unknown is quite important. So one of Bob's friends has a beard is existentially quantified because we're not specifying who. Whereas if we just say Emma is Bob's friend and has a beard, there's no quantification there. We're just talking about Emma and beards. So order matters. So I've got two logical expressions here, and all I'm going to do is switch around the order of these quantifiers. And in one case, we're going to say that everybody has some parent, which is true. And on the other hand, we're going to say that there's some person out there that happens to be everybody's parent, which is clearly false. Okay, quantifiers in programming. Let's start moving towards code. So we're looking at statements like this. I'm going to tweak the notation and the glossary a little bit. So I'm going to say that P is a type from now on. So we're just going to mark that like this. You can think of a type as a set of values, which means that this X is now going to be a term which you can think of as a value of having type P. So, code. Let's start with terms. Consider this function, wheatbix. Takes an int and a string and returns a boolean. Let's turn this into a logical expression. Only focusing on terms. So, okay, a wheatbix of A and B implies C. What else can we say about this? Well, A and B, they can be any ints and they can be any strings. What about the C? Does that have any quantification? Yes, it does. So there exists a C of type boolean. and that's the return type. And it's there exists because this could just constantly return true. It doesn't need the return false. You're only going to get one value out of it. So interestingly, this seems to map with variance. So if a term is in a contravariant position, then you use for all. If it's in a covariant position, you use there exists. Okay, let's move on to types. So the same function. This time we're going to ignore the terms and just look at the types. So we're going to have an int and a string gives you a bool, the in. So there are no quantifiers here. What would it mean to have quantifiers? Okay, so let's think of a type level for all. That means we're going to accept any type. This is the simplest logical statement you could probably come up with. For all types A implies A. Well, that's the identity function. All we do is introduce a type parameter here. And then it's just as simple as that. You just introduce type parameters for all, and then map them like this. Okay, so what about there exists? So remember, there are two criteria. It has to be at least one value, and that value needs to be unknown. Okay, here we go. We just declare that a value, a type exists, type A. So we're going to look at two slightly different bits of code here. So these two bits of code are identical, with the exception of that type A line. So on the left-hand side, we're not going to specify it. On the right, we are. We're going to say it's an int. Now consider this function. It takes a type, it takes a term t of type t, and then it goes t.a plus 9,000. The right-hand side is actually going to compile because the compiler knows that A is an int. That means we're dealing with a type alias. It's not actually an existential type. That type should be hidden, and it's a good thing if it is. And we can combine both notations and represent both types and terms in the same logical statement. So if we look at identity again, we can say for all types A, for all values x of type A, there exists a y of type A such that id of x implies y, sorry. Okay, the meat of this talk, examples. We're going to look at a few different examples here. So the first example is universal quantification for all. And I think most people, nearly all people, are going to be very familiar with this. This is quite common. We do this all the time in code. Therefore, I'm not going to spend too much time on it because it's not that interesting. If this is new to you, however, no worries. That's fine. Go and Google these things and have an awesome weekend learning about that. Existential quantification is a bit more underrated. So it's actually really great for certain use cases. It's great when you're describing things that have details that don't always matter or you want to hide them. It's also great for when you have data such that you want to have a high level, low resolution view sometimes, and then at other times you want to have a low level, high resolution view. So let's look at a contrived example. In this example, we're going to have a bunch of cases. Most of the time, we're going to use those cases generically, but then sometimes we're going to use them specifically. So we're going to build a survey/questionnaire app. So a survey has a bunch of questions. We give that to a user. The user responds with answers. How would we model this? Well, for starters, we can just say, well, for all questions, there exists an answer. And that's already kind of profound. What's the answer? I don't know. Depends on the question. We don't know the value. In this case, though, we'll create a survey type, and we'll give it two types. We'll say question and answer. And then we'll provide some implementations of this. So we'll have free text, in which case you can just ask the user anything you want. The question is going to be a string. When they type in their response, that's going to be a string as well. We'll define another type called multiple choice. And here you can ask them a free text question and then have a bunch of options. And the answer is going to be the index of the chosen option. Okay, so the first use case. Let's introduce JSON. Right, so we're going to add two functions now. We want to go from a question to JSON. That's always going to pass. And then we're going to want to go from read some kind of arbitrary JSON and then attempt to read a question back. So this is extremely simple. We just go to each case. And so here we're going to free text, and we're saying, well, we're just going to use a JSON string for that. Simple. The multiple choice takes up a little bit more code, but it's actually simple as well. We'll just use an object. It's going to have two fields, a question field and a choices field. So here's the kind of thing you end up with if you would use that. So here's a 3-question survey. What's your name? How many fingers do you have? And yeah, I won't read that. So there's a problem. Can you see the problem? Imagine trying to parse this back in. Generating it's fine. To really highlight this, imagine that somebody on your team adds a new survey type, which is, imagine there's some new service by Google that comes out called Google Surveys. And then your questions happen to be UUIDs that you query their database of questions with, and then answers will just leave as free text. Now look at this JSON, this survey JSON. I hope the ambiguity is clearer. String, string, string. Is it free text? Is it Google Surveys? So, very easily solved. Let's declare that all survey types have to declare a JSON type ID, which is just a string. And now we can generate JSON like this, and it's much clearer and unambiguous. So already we're getting some benefit out of modeling things this way. Normally, if you just had a typical ADT, you wouldn't be able to work out a type for something that you don't have an instance of. If, for example, one of your cases requires an int to construct, well, you don't have an instance to query. So a lot of JSON libraries will use magic, macros, and at compile time, they'll look up the class name and things like that. Here, we don't need any of that stuff. You can just, yep. Anyway, so generic JSON already looks nice, and we haven't lost our ability to just deal with specific cases. If we know that we're generating JSON for free text, and we're going to read free text back in, we can just use a string. So we can go to JSON, we can go back from JSON again. There's one more thing to do, which is how are we going to represent surveys? What's that type going to be? We know it's going to be a list of questions logically, but what do you mean by question? So if the survey type was the same, it'd be easy. We could have a list of free text questions or a list of multiple choice questions. But how do we represent this generically? In Scala, you can go survey type hash question, but that's completely useless because that's the same as just saying a list of anything because we don't have any constraints on what questions can be. So let's step back from code for a little bit. Think about this. Imagine if I told you, hey everyone, the answer's 10. That's completely useless. Nobody's lives have changed by that. Nobody has any new information really. On the other hand, if I said, hey, the question is, how many fingers do I have? And the answer's 10. Suddenly that's useful. Well, it's not really useful, but you knew that. But if you didn't know that, now you know. So you should think of, when you're coding, you're talking to the compiler, you're communicating with the compiler. And in the same vein, if you just tell the compiler, hey, the question's ABC of type string, that's useless to the compiler. It needs more information to be useful. If that's not quite clicking yet, imagine this. It could be a free text question or it could be a Google Surveys ID. How does the compiler know? It doesn't. Whereas if I say the survey type is free text and the question is ABC, suddenly this is useful. You can do something with this. You can make use of it. So let's model that in code. So we'll create a trait here. It's called and question, so survey type.and question. It's going to have two fields. One is a survey type, and then the other one's a question. Now, look at the types of those two. What we're doing here is maintaining that correspondence between this question that could be anything and the survey type. We're saying that the type is survey type.question. So yeah, it's important to manually maintain that evidence that you're dealing with something useful. Okay, and now we can go back to our survey and say it's a list of survey types and questions. Now to make this a bit more useful, we'll go into our survey type trait and we'll add two things. We'll add a type alias to say also called and question, and all we'll do is say it's a survey type and question, but the survey type is itself. Similarly, we'll add a method to create new instances where all you do is pass in the question. The question is tied to your own survey type, and then you get and question with that association that it's your own type of question out. So then usage looks like this. We can go free text dot and question, pass it a string, all those types check out, and even the return type matches. It's a free text and question. And then if we want to deal with this generically, we can just, not really cast, but we can explicitly tell the compiler to forget that free text information. We'll say this is a survey type and question now, so we've just lost that refinement. Cool, we've ticked all the boxes. Use case number 1 complete. Use case number 2. Now we want to ask the user questions, have them type in an answer, and then we're going to, for a full survey, and then we're going to create a big JSON with all the questions and all the corresponding answers. So the first thing we'll do is add functions. So in the same way that we had JSON functions for questions, we'll just add that for answers, nothing different there. A new thing that we'll add is this ask user function, which it'll take a question and it'll return an IO of answer. And just imagine that it's just gone to the console and asked them to type something in. So just for convenience, I'm also going to go back to our generic survey type and question trait. I'm going to add 2 fields to that. One is a type answer, and then just say that's equal to survey type.answer, so the user doesn't have to type that in all the time. And then, because we already know what the question is, because we're passing around the survey type and the question, we're just going to pass that question to the survey type, so we get a nice IO of answer. This is just for convenience. Now, let's say this is the kind of JSON that we want to generate. 3 fields, type as text, question, and an answer. I won't show you the code because I was worried about running out of time, but this would be the type signature. So you take a survey type and a question, and then you just ask for a dependently typed answer, q.answer, and then you return a JSON. And it's really trivial to generate that. Okay, done. Now we execute the survey. We use every functional programmer's favorite tool, traverse. We just traverse over the survey. We ask the questions, ask the user the question, map their answer back into that Q&A JSON, and then just turn all that into a big JSON array. Done. Very easy. So generic use works very, very well. Throughout all of this code, we're never dealing with the specific question types, nor the specific answer types. It doesn't matter. We've got full type safety in that each answer is associated with each question, and each question has a corresponding survey type. And we don't have to do any casting or coercion or anything either there. So, specific use. Imagine your boss comes up to you, as bosses do, and say, hey, we need a special customized app for some team. We want to ask them their name, we want to ask them their age range, and then I've got this special means for you to compose those 2 specific answers. It's as easy as this. So let's read through this. First of all, we just say Q1 equals a free text and question. There's a question. For Q2, we say it's a multiple choice and question. And then in a for comprehension, which is like do notation in Haskell, we just monadically ask the first question, ask the second question, and then we compose them according to this specific rule that he's given us. Or she. So it's important to note here that we know the types. We know that question 1's answer is a string in this block. We know that question 2's answer in this string in this block is an int, which is exactly what you would expect. And again, we've got full type safety, no casting, no coercion, nothing like that. Okay. So I've got a learning repository online. You can find all of this code here. It's much more fleshed out. Everything's there except for the implementation of the ask user function, which you can implement yourself for fun. Okay. Now, water quickly. On to our third and final example. Scala.JS-react. So you've heard a little bit about React already. React is a JavaScript library for building user interfaces, mostly websites, right? Scala.JS-react is a library that builds on top of that and makes it as type-safe as possible and makes it a very FP experience. And that's my library, by the way. Just want to talk about it. So React at its heart is actually FP. So the way you use React is you create a component, which is like a UI widget. And what that'll do is have a type parameter P, which is props, and then a pure function from props to virtual DOM. So this is an example of that. So say our props in this case is a person class, which has a first name and last name. In the middle, there's our pure render function. We just take that P and generate some virtual DOM. And then when React's ready, it'll turn that into real DOM and real HTML like this. Oh, okay. Okay. So React has this performance optimization called should_component_update. It's a function that takes two P's and returns a Boolean. So just before calling your component's render function, it'll give you the previous props used and the props that it's about to use now, and you've got a chance to compare those and potentially just say, no, I don't want to update, let's opt out of further processing. So typically the logic that you'd use when you're implementing this is you say, okay, I've got both of my props values, I'm going to compare them. If there's no change at all, then I don't need to update the component. So looking at this, you might think a potential solution in Scala is to just use an equality type class and then negate the value. If they're equal, no need to update. But in the real world, it's not so simple. It's not, you don't always just use the result of equality. This is a performance optimization. In some cases, full equality might be very slow to calculate, whereas you just want a less accurate, really fast function instead. Similarly, you might just want to compare if you've got if you've got a really big model, you might just want to look at the ID and say that's it, if it matches or if it doesn't. If you're using floating points, you might have some kind of tolerance. With timestamps as well, you might want to say, I don't care. I don't want to update unless the timestamps grow beyond 1 second apart. So, how was I to support this in Scala.JS React? Well, I did what any good functional programmer would do and use the type class. So, very similar to equality, I created something called reusability. And now, given reusability, I can compute a should_component_update function. Okay, so we'll just add a few type class instances to the library. So we'll say, so you're already seeing quantifiers here, by the way. So for all strings, we can solve this problem by using just universal equality. For all lists, I'm going to say use reference equality because that's really fast, and then if not, iterate through both lists and compare the elements. There's also a derivation macro for ADTs. And let's try this out. We'll go back to our person, we'll add a list. It works, great. Except it doesn't always work. So in FP, when you're dealing with side effects, what you do is you want to make your code as pure as possible, so you push side effects all the way to the boundaries. I actually advocate for a very similar approach when you're writing React. React components can be stateful, optionally. I advocate that you make them more stateless and push that state all the way to the component boundaries as well. When you program in that manner, you end up passing around functions a lot. So this is a very realistic kind of function. A UI component wants to update its name. Well, it takes the new name as a string, and then there's some kind of side effect that happens. It doesn't care about what that is. So we don't have reusability for this. How do we provide that for all functions? Similarly, if you imagine there was just a little save button, you click it, you want to execute some arbitrary I/O. How do we define a reusability type class for all I/O? There is no universal solution, but I thought to myself, well, if I take care to create a single instance of these and take care to reuse it as well, then reference equality will hold. A different way of phrasing that, because that's quite easy to do, by the way, a different way of saying that is that we can't solve this for all terms, but there do exist terms such that it's solvable. So let's look at what we have. We've got a should_component_update function that, I'll read the logical expression. So for all types A, if we have a reusability of A, then we have should_component_update for A. what we want is to say, well, there exists a type A, there exists a term of type A, and if we can define reusability for that term X, then we have should component update for A. The problem is, reusability, that's a type class. It doesn't take terms, it takes types. So, how do we solve this? We'll start from the same starting point. So, we've got the term. We know that reusability needs a type. So, okay, let's introduce one. We'll just say there exists a type B such that it has reusability. Now we're going to say there exists a value Y of type B. And then, if we have a function that can take an X of type A into a Y of type B, then we have should component update for type B. So I'm just going to take this and turn it into code bit by bit. First of all, the structure. So there exists a type B. Here we go, case class B. It has reusability, and then we know that we want to take an X of type A into a B at some point. Next, we don't actually want to lose our A value in this process. So we'll add that in there and make sure that we retain it. So suddenly B is parameterized by A now. Next, the whole point of this is that we have a means of term reusability. So, okay, let's pass that in our apply function, and we'll save that. And if you notice, instead of an A and an A to a Boolean, it's just an A to a Boolean because we know what one side of this is. We know the term. And next, let's implement reusability for this, the type class. So, given two values, we'll just call this reuse function and compare them with each other. And if they're both happy that the other side can be reused, then we're all good. And next, we'll just give it a sensible name. So instead of B, this is called reusable. Great, success. Now, back to our original use case. We've wrapped our update name and our save fields in reusable. And yeah, derivation works. It all compiles. I'm going to quickly add a convenience method to reusable to say by ref, which will use reference equality. Here you can see all I'm doing is just taking that term and then generate the function. Right, and then at the call side, what we do is we wrap the types in reusable, and then we specify our means of reuse for that term. So here I'll just say reusable by reference equality, pass in the function, or pass in the IO. Oh yeah, and then that's it. We're golden, all works. Right, so if you have a look at the Scala.JS-react repository, you can see search for reusable.scala, you can see all the code there. And it looks very, very different now than it does in this talk, because it's gone through a lot of evolution that has more features to it. All right, success. So we've solved this problem for all types. And what I mean by this is that we don't need to add any more solutions for new types when we want to bring them on board. So you opt in with types by declaring a type class instance. So there's just types such that they have reusability. We've solved it for all terms belonging to types that have reusability, and we've also got a means to solve this for certain terms and not others. Great. So a summary, just to summarize. So existential types are opaque. Existentially typed solutions often require manual evidence propagation, and that's what I mean by maintaining that correspondence yourself. Existential types are great for high and low detail. For all types is actually parametric polymorphism. Type classes are there exist types, such that for all terms. Terms in contravariant positions are for all. And the above 2 points can be circumvented by using a dedicated type, and that's what I did with reusable. Terms in covariant positions there exists, and solving for all and there exists separately can be a very good practical solution. And in a very large, very complex code base, this has worked tremendously well. Whereas before I came up with this, I was constantly finding the solutions I was coming up with not very good and trying to reinvent it all the time. Since this, I've just been happy. So thank you very much. Very soon the slides and code will go up on this repository. Thank you.